Hi everyone, welcome to Mostly Math. Today I'm going to show you how if we evaluate one really simple contour integral, we can get two really complicated real integrals out of it. Let's begin by considering the integral here, I integrating over some circle of radius a in the complex plane with respect to z of e to the z over z. So let's look at our pole chart here. We have one pole at the origin, and we're going to go counterclockwise in a circle of radius a. This is pretty easy to evaluate by the residue theorem. There's only one pole, so the residue at z equals 0 of our function is just going to be the function multiplied by z, which is e to the z, evaluated at z equals 0, which is 1. Pretty easy. If we multiply this by 2 pi I, we get our integral. 2 pi I times the residue at z equals 0, which is just 2 pi I. Well, that's great, Brandon. You evaluated a contour integral. Congratulations, you know the residue theorem. So what? What does this tell us? Well, if we parameterize this, separate it into real and imaginary parts, we can get two pretty difficult real integrals. Let's see how. So, let's begin by parametrizing by z equals a e to the I t, where t is going to go from 0 to 2 pi. Obviously, a has to be greater than 0 for this to work. And let's go ahead and rearrange some stuff here. We now know that 2 pi is equal to this integral here, 2 pi I rather. And we now let the bounds go from 0 to 2 pi. We need to differentiate dz here, which is pretty straightforward. Becomes I a e to the I t dt for our dz. And e to the z is just e to the a e to the I t. Pretty cool. We have a nested exponential there. Dividing by z, we get some cool cancellations here. Just becomes I integral from 0 to 2 pi dt e to the a I t. And we can cross out this I now. So we have our first result. 2 pi is equal to that integral up there, which is e to the a e to the I t. Pretty cool nested exponential. So now you might be saying, okay, we just have the real number on the left, and we also have a parameterized form. So what? How does this help us evaluate a real integral? You told us you'd evaluate some real integrals. Well, why don't we use Euler's formula a couple times, and let's see what happens. All right. 0 to 2 pi with respect to t e to the a cosine t plus I sine t, of course. And go 0 to 2 pi e to the a cosine t e to the I a sine t. Let's go ahead and use Euler's formula again. Just going to be integral from 0 to 2 pi dt e to the a cosine t times the real part, cosine of a sine t. We're going to have I times the imaginary part, another integral now, sine of a sine t. Now this is where things get interesting. We have a real number on the left, and we have two integrals on the right. a plus ib. This is just a really fancy a plus ib. So we can set the real and imaginary parts equal to each other. Immediately, we can deduce that 2 pi is equal to the first integral here. And 0, interestingly, is equal to the second integral here. Well, there you have it. We can pretty much stop here if we want to. I told you we'd evaluate 2 integrals, and we have. Pretty cool. Some notes about this. This formula is only valid for a greater than 0. Both of the a's have to be the same, of course. And notice it's a family of integrals, so not just one integral, but because we could have the radius of the circle be anything, we actually got an infinite family of integrals as well. And these are pretty difficult. I want to say it is possible to go the other way, like you start with this integral and then reverse the steps of applying Euler's formula. It's certainly possible to do it that way as well. I just think that this way is easier. It's also probably the way that these integrals were first derived, because it doesn't make much sense to consider these integrals by themselves. They're so weird. But the original contour integral, you know, e to the z over z is pretty easy function to try to integrate. Okay, let's go a bit further. So some questions I had while I was evaluating these integrals is, let's look at the graph to motivate some questions. Yeah, let's look at the graph to motivate some questions. And rewrite a few things. So I'll result, I'm going to rewrite them. First result, second result. Okay, sounds good. Let's look at the graph of these functions. 0, pi, 2 pi looks something like this, like a weird wobbly horseshoe thing. And on first glance, it appears that this area should be equal to this area. They should both be equal to pi. Is it? Is it though? And second graph here. God, I don't have enough room, do I? Looks like a weird, more curved sine function. So again, we would postulate that these areas would be equal, so that if we add them together, they would be 0. This is not as simple as it sounds, because even though this is an even function and this is an odd function, we're not currently integrating it over a symmetric domain, like minus pi to pi, to be able to conclude such things. But there is two ways that we can do it. First way, using complex analysis. I really shouldn't have erased that final step here. 2 pi is equal to t plus I We can use the geometry of the complex plane to actually change the bounds of integration with no difficulty at all. So we currently let t go from 0 to 2 pi. This is okay because it goes counterclockwise and covers the whole circle. But why not let t go from minus pi to pi? We can also do that. It doesn't change anything except the limits here in this last step. Let's go ahead and change that. And now we can conclude that this integral, first one, is just twice this integral. Because it's even, and we don't actually know anything about this integral. It's 0 because we know if we have a minus a to a integral of any kind of odd function, it's going to be 0. This is obviously odd. So we actually get a second result as well, that pi is equal to integral from 0 to pi dt e to the a cosine t cosine a sine t. And we know that we actually don't know the value of this integral, but Wolfram alpha tells me that it is approximately 2.1. And if it doesn't have a real form of it, I don't think one exists. So we have another result here, which is pretty cool. We just invoked the geometry of the complex plane to do it. But a question that bugged me while I was evaluating this integrals is, isn't there a way to do this analysis without going back to the complex plane? Like just have this integral here and then put this area on top of each other to show that they're equal using purely real methods. Yeah, you can do it. I thought it would be better, but it's not. I'm going to show you why it's not. So the rest of the video is pretty much an aside. It's not related to complex analysis, just some ordinary change of variables. So to the viewers that don't want to proceed further, I understand. Have a great day. Main result is as we have the one complex integral, super easy. You get these two really hard real integrals. Anyways, let's proceed. Okay, gang. Let's begin with our main integral here. What we want to do is basically take this area on the right and put it on top of the area on the left to show that they're equal. And to do this, all we have to do is write what we know so far. 2 pi is equal to, we're going to break it up now. Integral from 0 to pi plus the integral from pi to 2 pi of our integrand. Okay, the rest of the analysis will be concerned only with the troublesome second integral. So for this integral from pi to 2 pi now, we're going to make the following substitution. Let t go to 2 pi minus t. Geometrically, this just folds the area onto each other. And if you can't see that, like I couldn't see it, you will see that it changes the limits like we want it to change. Since t now goes from pi to 0, and dt will go to minus dt. We can see already how things are going to work out for us. This integral is now pi to 0 minus dt e to the a cosine of 2 pi minus t cosine of a sine 2 pi minus t. But wait, I don't remember all these stupid formulas from high school about adding pi's to cosines and stuff. That's okay. I can show you how you can always derive them. Consider e to the I 2 pi minus t, right? Yeah. If we do this, it's just e to the 2 pi I times e to the minus t. This is 1, of course. It's just cosine t minus I sine t. So we see that the cosine doesn't change if we do this. Sine gives us a minus sine. And that doesn't matter because the cosine is an even function. So this integral is 0 to pi dt e to the a cos t cos a sine t, which schematically is our integral 0 to pi. So our result, I have to erase it. Yeah, have to erase it. I don't have enough room. Tells us that this is just twice integral from 0 to pi dt ea cos t cos a sine t, and we can cancel the 2's. We did all of that to show that we can cancel the 2's. Okay, granted it's not that hard, but it's a lot harder than simply changing the limits like we did in the complex case. Now let's do the same thing with the other integral here. We want to show that these integrals are equal. So we're just going to change a few things. Replace this with sine. And we don't have this being equal to anything. We're just evaluating it. Integral from 0 to 2 pi of our integrand is just equal to this. Again, we do the same thing. Everything is pretty much the same, except one important difference. We have a sign here, so this becomes minus sine t, and sine of that brings a minus sign out front. So this whole thing is equal to minus the integral from 0 to pi. God, that's a lot of writing, this damn integrand. Okay, so the whole thing is equal to 0 to pi of something minus the integral of 0 to pi of something. I'm tired of writing the integrand. I'm not going to write it anymore. It's 0. It's 0. Because they're equal to each other. So I had to go through this real world to satisfy my curiosity that it could be done. It can be done. I think it's a lot cooler to simply change the limits, invoke the unit circle in the complex plane. That's basically all I have for you today. So if you enjoyed that, want to see more, please subscribe. See you next time.